Soil dynamics. Welcome to your tape. Just kidding, guys. Welcome to our Edpuzzle post about soil dynamics. This information that we're going to cover in this video can be found in Chapter 8, Module 25. So definitely look at that to build upon your understanding about this topic. So a quick review about where we've been. We've talked about weathering and erosion. We talked about how that contributes to the recycling of elements. So rock is exposed to Earth's surface, it's broken down through weathering and erosion, and then it's moved around, it's put back into the mantle at some point or another just so it can cycle back through. So we've talked about weathering and erosion, but what is weathering and what is erosion? So first we're going to talk about weathering. We'll talk about physical weathering. So physical weathering is the mechanical breakdown of rocks and minerals. So the actual breaking down of rocks and minerals physically. So examples of this, ice expansion, which we saw in our lab when the ice expanded within the glass vial and broke the vial apart. We see that in nature through the water seeping down into rocks, freezing and breaking the rock apart. We see that in our lives through potholes, which we've talked about. Another example of physical weathering is an organic weathering, so roots making its way down into rocks and then breaking that rock apart. We're going to see that in our lab later when those beans start to sprout and break apart that rock simulation that we have in there. You might see this in your everyday life through jankety sidewalks. So where that tree root is moving underneath the sidewalk and it grows and expands and then displaces that sidewalk, that's an example of physical weathering. Chemical weathering is the breakdown of rocks and minerals by chemical reactions, the dissolving of chemical elements within the rocks, or both. So the perfect example of chemical weathering is something that you all are familiar with, acid rain. But really, it's not just acid rain, there's acid snow as well, which sounds a little weird because we usually think that snow is really pretty and light and fluffy. But when we talk about both acid rain and acid snow, we're going to talk about acid precipitation. So acid precipitation, can't say it, is precipitation that's high in sulfuric acid and nitric acid. And it's important to know that sulfuric acid and nitric acid are the two acids that make our rain acid precipitation or our snow acid precipitation. So this occurs when in the atmosphere, water vapor reacts with sulfur and nitrogen oxide. So that's what's going to make it form that nitric acid and sulfuric acid. And then it comes down to our earth in the form of acid precipitation, and it's going to alter primary minerals. So primary minerals are those that are newly exposed to their surroundings, newly exposed to our troposphere. And when those chemicals interact with that primary mineral, it's going to turn it into a secondary mineral. So some examples of that. Granite is an example. Lichens on tombstones, the Statue of Liberty. So this sounds really negative, but it can actually be good. A perfect example of how acid precipitation is positive is its formation of granite. And we know through studies that granite is great at absorbing carbon dioxide from the atmosphere. So with acid precipitation, you get your good and your bad. Here are some pictures that are examples of acid precipitation's effects. So here on the right, you see the Statue of Liberty. You see the top of it is that nice bronze color that it would have been when we received it from France. And on the bottom, you see what it looks like today. It's that green color. It's that rusty color. And we will see that in our lab through those pyrite chips that we're letting sit over the weekend. Those chips you will see more of a chemical change in as well. Here's an example of more acid precipitation effects. You have a statue on the left with its face still fully intact. And then on the right, you see it faceless and kind of creepy looking. So this is an example of how acid rain and acid snow over time has broken down this rock and made it a smooth surface. You might have seen this through your marble chips and granite chips that you submerged in hydrochloric acid. So you saw that those edges weren't quite as defined anymore. So now that we've talked about weathering, let's talk about erosion. So what is erosion? So this is the physical removal of rock fragments from a landscape or ecosystem. So we're taking rocks away from an ecosystem and moving them somewhere else. So there's two ways that this is going to happen. The first way is that wind, water, or ice are going to move the materials down slope. So we see wind through things like dust storms. We had the Dust Bowl in the Midwest. We see it through water. Rivers are going to take sediment and deposit it downstream. Ice, we looked at glaciers in our lab. That's going to move rock material from one place to another. Another example is an organic process, another organic process. So this is when living organisms are going to burrow under the soil. So they're displacing that soil from its original place and moving it somewhere else. So erosion, while sometimes erosion is not so great, especially when we're looking at things like sediment deposits in rivers, which we'll talk about much later in the year when we talk about water systems, this can cause some pretty beautiful things. An example is here in the Grand Canyon, the Colorado River has carved this snake-like trail through the Grand Canyon, and it forms this beautiful landmark, really. Another example is on Oceanside. So these rocks that have had little arches form in them throughout the years due to water beating that rock and breaking it down slowly and moving that rock somewhere else. Last example, beautiful example, this little burrowing owl. This is an example of an animal that's going to burrow underground to make its home. Maybe you've seen these before if you saw the movie Hoot or read the book, a classic. So we know all about this rock cycle, and now we need to know how it links to the biosphere, how it links to us, how it links to what we're about to study in the future in this class. Soil. Soil is that missing link. So soil has many functions. It's a medium for plant growth. You see in this picture here a tree growing in the soil. It's a filter for water. It's a habitat for living organisms. And it's going to be a filter for pollutants. So all soil is going to have three properties. It's going to have physical characteristics, texture, and permeability. So these physical properties are like the size and weight, its texture, its permeability. Again, I already said that. And all of this depends on the amount of sand, silt, and clay within the soil. All soil has sand, silt, and clay in it. This pyramid is your new BFF. This pyramid is going to be used to find out what type of soil you are looking at. So maybe you didn't know there was more than one type of soil. So you can see on here there's clay, there's clay loam, there's sandy loam, loamy sand. There's so many different kinds of soil, and each one of those have unique properties due to the amount of clay, silt, and sand that are within them. In our lab, we will look more so about how to read this pyramid. So permeability of a soil depends on the texture. It's going to depend on the amount of sand, silt, and clay in it. So this image kind of shows the relative permeability of each of those three materials. So you can see here that sand is pretty permeable. So after an hour, water is going to start permeating through those sand particles, making its way through, and that jug would be able to drain. Silt, with those medium-sized particles, is a little harder for water to permeate. So it'll take about 100 days for it to start permeating through and leaking out. Here you see clay. Clay is nearly non-permeable. So you can see here that after 100 years, water would not start leaking through this clay if it was just pure clay. That's because these particles are so small and so densely packed together that water isn't able to make its way through. So what does this look like? Soil, if you were to take a little section out of it, has different horizons. So we have our O horizon first, and that's organic material in various stages of decomposition. So you have dead plants, dead animals, all breaking down, and they're all in various states of decomposition. Then you have your A horizon, which is also known as topsoil, and this is kind of mixed with overlying organic material and underlying mineral material. Usually you will not have both an O horizon and an A horizon. It's an either or. You either have O or A. Underneath one of those two is the E horizon. So this is a zone of leaching metals and nutrients. So again, it's either under the O or under the A. This is also where you would begin to find acidic properties of soil. Acidic properties are not always negative. Some plants prefer acidic soil. Next is the B horizon, which is the zone of accumulation of metals and nutrients. And then last is the C horizon, which is the subsoil, and it's the least weathered portion. It's going to be the most similar to the parent material. And the parent material is really the type of rock that has been broken down to form this soil to begin with. So, we know from the beginning of this unit that when Earth was formed, we had a predetermined amount of minerals and rocks and different elements. But what we haven't looked at yet is how those are distributed throughout the Earth. So they're not equally distributed, and that's important. And that's important because it has social and environmental consequences. And when I say social consequences, I mean social more so as socioeconomic consequences. So we know that rocks and minerals are finite resources. Once we use them, once we chemically alter them, they're done. We've used them. So like in our use of coal, we know that once we've mined it, once we've burned it for energy, it's gone and we cannot replenish it. And some of these minerals that we have are abundant. We have a lot of it. We've used a lot of coal. We still have a good amount left, but some are really rare. And when we look at these rare minerals, this is even things like diamonds. Mining for diamonds, they're so expensive because they're so rare. So you can probably see why this might have a socioeconomic advantage or disadvantage. So where you live on Earth kind of depends on what resources you have. So this really lends its hand into trade and global trade, having to buy and sell different resources from one area of the world to another. So it's definitely important where these different rocks and minerals are distributed. So we're going to look now about the abundance of ores and metals, and we'll talk about what ores are and what metals are. So ore is a concentrated accumulation of minerals from which economically valuable materials can be extracted. Perfect example of this, iron ore. Iron ore is mined and later turned into steel. So steel is very valuable, so you can see why this one might be important. Metals are an element with properties that allow it to conduct electricity and heat energy and to perform other important functions. Examples, gold, copper, both things that are very expensive and in very high demand. Gold, not so much anymore. But still, copper, we use copper wiring because it's a great conductor. So, you might have heard people talk about before our gold reserves or our iron reserve or the reserve bank. So, reserves are the known quantity of a resource that can be economically recovered. So, how much money do we have in gold is really what that means. So, we know we have this stuff in our crust. So, what's that makeup of it? Oxygen is overall the most abundant element in our crust, followed by silicon, aluminum, and iron. This table here shows the approximate supplies of the metal reserves remaining. So here you can see the global reserves remaining, how many years, if we continue with the use that we have now, how many years is that going to last us? And then you look at how much the United States have. I think aluminum is the cool one here. This just shows how little aluminum we have in the United States. So the rest of the world is 330 years worth. We only have 2. So this really shows why it's important for us to trade with one another, why those economic principles are really important when it comes to the distribution of metals and ores. So that's all the time we have for this video, but stay tuned and move to soil video 2 to hear some more.